First of all, I would like to thank the organizers for giving us the opportunity to present this work. This work is in collaboration with Kornell and Mislove, and we all work at Tulane University in New Orleans. To give a very short summary of this talk, we aim to introduce a category of so-called quantum CPOs with the purpose of to use them for denotational models for quantum programming languages. In particular, we were inspired by Rios and Salinger's Proto-Clipper M, but we aim to use this category for a broader class of quantum programming languages. In particular, it's designed to support recursive data types, and it's obtained via the program of non-commutative geometry, and as a consequence of the latter, we can regard this category as a quantized version of the category of CPOs and Scott continuous functions. So what are recursive types? Those are basically types that are defined in terms of themselves. And they're often denoted as mu of x dot t, where x is a type variable. And the intuition is that that the type is a solution of an equation of the form x is isomorphic to t of x, and such an equation is called the domain equation. And as an example, the natural numbers form a recursive type, which can be denoted as mu of x identity plus x, but also lists of elements of type A can be described as a recursive type. And the nice thing about recursive types is that if a language has recursive types, then typically it also has recursive terms, which means that you can use general recursion if you are programming with it. And sound models of languages with recursive types should allow to find canonical solutions of domain equations. And that is exactly what we hope to achieve with QCPO. So what is necessary for a model for quantum programming languages? So first we need basic types like qubits and bits, and the first are typically represented by 2x2 matrices. But we also want to describe combined systems of n qubits, which is typically described by taking the n-fold tensor product of 2x2 matrices, and the result is again a matrix algebra. In most programming languages, conditional branching is represented by the coproduct. In case of matrix algebras, that's just their sum. And it's a theorem that all finite dimensional algebras over C are isomorphic to a finite sum of matrix algebras. And as a consequence, we require that any categorical model for a quantum programming language should contain the finite dimensional algebras as a subcategory. In order to support function types, we want L to be symmetric monodal closed. It should also represent conditional branching, so we should have coproducts. And in order to extract classical information from the objects, which you typically want with quantum programming, you need a comonad on L, which is typically referred to as the bang. And any such category induces a so-called linear nonlinear model, and that consists of a Cartesian closed category and a symmetric monodal closed category and a strong monodal functor between them, which has a right adjoint. And this adjunction induces a comonad, which is the bang. And then again, for quantum computing, the finite dimensional algebras should be a monodal subcategory of this category L. And in particular, models for Proto-Clipper M are known to be linear nonlinear models of this form. Okay, we want to promote a certain recipe in order to obtain models for quantum programming languages. And the first step is by taking the classical fragment of the language. And then we find an appropriate category which models this fragment. And this category is typically a Cartesian closed category. And then the next step is quantizing this Cartesian closed category according to the principles of non-commutative geometry. And The resulting category is a symmetric monodal class category. We refer to this category as Q of C, quantum C, and this category typically also contains the finite dimensional algebras as a subcategory. Furthermore, there's an embedding of the original category into the new category, which happens to be the left adjoint of a linear nonlinear model. And yeah, this is basically how we get our models. And these models we call non-commutative or quantum models. And they are in some sense more natural than other models, such as pre-sheaf models. For instance, in the latter, the monodal product is the day convolution, which is really hard to calculate. Whereas in quantum models, the monodal product is way more simple, and it has also nicer properties. And because of these properties, adequacy results are within reach. Okay, what is non-commutative geometry? So it's basically a program to find natural models of quantum structures. And the main idea is that you start with algebras of operators on the Hilbert space, because they typically are used to describe quantum systems. And then, yeah, we construct non-commutative generalizations of classical structures. Classical structures correspond in this framework to commutative algebras. And so if we equip our algebras of operators with extra structure, then the commutative case should correspond to the original classical structure. Now, typically you get some category of operator algebras, and the dual of this category can be seen as the non-commutative generalization of the category we wanted to generalize. But this dual typically does not have a concrete description. And as an example, we can look at Galvan duality between compact Hausdorff spaces and commutative unital C-star algebras. So we have for every compact Hausdorff space X, we can look at the C-star algebra of all complex valued continuous functions on this compact Hausdorff space, and that's commutative unital C-star algebra. And, as a result of Galvan duality, we can consider the dual of the category of all unital C-star algebras as the category of non-commutative compact Hausdorff spaces. But until now, nobody knows how to give a concrete description of this dual. Okay, so next we are looking at FPC. This is, it stands for fixed point calculus. It was introduced by Plotkin, and it's a classical meta language with recursive types. And we are interested in this because if we're looking at quantum programming languages with recursive types, and then if we look at the classical fragment, it should be quite similar to FPC. And hence, if we know what the models are for FPC, then we know how to find the quantum version of that. So models are typically constructed in terms of the category CPO. This is done by Fiore in his PhD thesis. But CPO also plays a role in the extension of FPC with linear types. This resulting language is LNL FPC, the linear nonlinear fixed point calculus. And typically adequate models for this language are CPO enriched linear nonlinear models. So also here CPO plays an important role. LNL FPC, by the way, can be regarded also as a circuit-free fragment of Proto-Kuiper M extended with recursive types. So this again gives a link between quantum programming languages with recursive types and classical fragment FPC. So bottom line is we need to find a way to quantize CPO. And the first step is, since the CPO has an underlying set, is to quantize sets. Now, it's known that von Neumann algebras can be regarded as the dual of a category of non-commutative measure spaces. And well, a measure space is a set with extra structure. We don't need that extra structure. Hence, it turns out that we can find a subcategory of von Neumann algebras, which can be seen as a proper non-commutative generalization of sets. And this category is the category of hereditarily atomic von Neumann algebras. These are basically von Neumann algebras isomorphic to possibly infinite sums of matrix algebras. Here you see L of HI, the operators on Hilbert space HI, and if HI is finite dimensional, then this L of HI is isomorphic to a matrix algebra. And the nice thing about this category of W star hereditarily atomic von Neumann algebras is that its dual has a concrete description, and this is the category of quantum sets. Well, quantum sets were introduced by André Kornell, and a quantum set is basically a collection of finite dimensional Hilbert spaces, and the Hilbert spaces are called the atoms of X. And just like we can define relations between ordinary sets, we can also define relations between quantum sets. And that's basically a function that to each atom of X and to each atom of Y assigns a subspace of the operators between X and Y. So these binary relations on quantum sets were also introduced by André Kornell, but I have to mention that they're essentially the quantum relations on von Neumann algebras, which were introduced by Nick Weaver. Now, just like we can order ordinary relations between ordinary sets, they are basically sets themselves, so we can order them by inclusion. We can also order binary relations between quantum sets. And moreover, the category of quantum sets and binary relations is Dagger compact. And that might be interesting for the people who work in categorical quantum mechanics. And moreover, we have a fully faithful functor. We have an embedding of the category of ordinary relations into the category of quantum sets and quantum relations. And this functor preserves the Dagger compact structure and the order between relations. And this is very important because many structures in mathematics can be described in terms of the Dagger compact structure and order between relations. And this gives us a way to generalize ordinary mathematical structures to the quantum world. So for instance, a function between quantum sets is a relation satisfying following two inequalities. And if you look at what the definition is of an ordinary function between ordinary sets, you want to express this in terms of the Dagger compact structure of the category of relations, you get exactly the same inequalities. Now, so we get a category of quantum sets and functions, and this is symmetric monadal closed, as shown by André Kornell. And it's dual to this category of hereditarily atomic von Neumann algebras. And furthermore, we have again an embedding of set into Q sets, and this embedding is the left adjoint of a linear nonlinear model, and this model can also be used to model Proto-Kuiper M. Next, we are going to look at quantum posets. So this is another example of using the Dagger compact structure of quantum relations and just mimic the constructions in relations, the category of relations. So basically, we give here the axioms of an order on a quantum set, but if you look at the axioms of an order on an ordinary set, and you express it in the Dagger compact structure of the category relations, then you get exactly the same inequalities. And also we can express monotonicity of functions in terms of the order between relations, and this is exactly the same in the ordinary world. Now, an example of quantum poset, we take the quantum set which has only one atom which is two-dimensional, and we call this quantum set H2. And this is an important example because this quantum set represents a qubit. Now we can define a relation on H2 in the following way, and this is an example of an order on H2. Okay. Next, we remark that if we have two functions from a set into an ordered set, then the order on the ordered set induces also an order on these functions. And in the quantum world, it works exactly the same. If we have two functions into a quantum poset, then the order on the quantum poset defines also an order on functions into this quantum poset. This is important because now we can formulate what monotonically increasing sequences of functions into a quantum poset is. And if there is a function k infinity such that this intersection property holds, then we say that this function k infinity is the limit of the sequence. And this is the quantum analogon of monotonically increasing sequences in ordinary posets, and this describes the supremum of such a sequence. So we call this a limit, but k infinity in this case is also the supremum of the kn with respect to this order we defined above. But generally, a supremum is not necessarily the same as a limit. So in the quantum world, things are slightly different. Now we can define what a quantum CPO is. That's namely a quantum poset, such that if we take a natural number d and we look at the quantum set which contains only one atom of dimension d, then given any monotonically increasing sequence of functions, there should be a function which is the limit of this sequence. And then we can also define when a monotone function between quantum CPOs is continuous, namely if it preserves these limits. And again, an example, namely any quantum poset with a finite number of atoms, such as the poset in the previous example, turns out to be a quantum CPO. And it's the same in the classical world. Any poset with a finite number of elements is a CPO. Well, the category QCPO turns out to be monodal closed, has all limits, has all coproducts, has omega colimits over embeddings, and it's enriched over CPO with respect to this order we defined previously. And again, we have an embedding of CPO into QCPO, which turns out to be the left adjoint of a linear nonlinear model. So far, so good. But if we want computational adequate models, then we require the denotation of non-termination. And classically, that's done to look at the category CPO bottom strict of pointed CPOs and strictly Scott-continuous maps. And then the bottom of any object here is used to denote non-termination. Well, CPO bottom strict is a subcategory of CPO. And in a similar way, we can find a subcategory of QCPO, which we call QCPO bottom strict. It's symmetric monodal closed. And basically, it's the quantum generalization of CPO bottom strict. And we have a linear nonlinear adjunction between CPO and QCPO bottom strict. Hence, this is a model for quantum programming. And moreover, it turns out to be CPO algebraically compact, which means that any domain equation involving a functor, an endofunctor, which is a CPO functor, can be solved. Now, moreover, we have the functors, the bang, the tensor product, the coproduct, and the monodal closure. These functors are used to represent the most common type constructors, and all these functors turn out to be CPO functors, so any relevant domain equation can be solved. And as a consequence, we find that this model is computational adequate nonlinear types for LNL FPC, and it's a sound model of proto-Kuiper M extended with term recursion. Those were basically plug-and-play results, but we expect that this model is also computational adequate for proto-Kuiper M extended with recursive types. And with that, I would like to end. Thank you for your attention.